Thank you very much. I hope you can hear me well. I see you in the dark, but this is good because that's how space is. It's dark. And it's the first time I give a lecture in a planetarium. And planetarium is probably one of the best things, one of the best places to speak about the future, because everything you see in a planetarium is billions of years old. And it gives you a little bit of a perspective when you speak about the future. I'm going to speak about the future 10, 15, 20 years ahead. And what you see in a planetarium is typically billion of years old. It also gives a certain personal touch, because you know that everything you touch and everything you are made of, and I'm made of, and we all are made of, has been produced in these stars. In one of these stars, we are all nothing else than some organized stardust, sometimes more, sometimes less organized. But let me come to the lecture. I'm going to talk about the future. I hope you have seen the lecture that my colleague Mark McCaffrin has given yesterday at the opening festival. He spoke about why and how Europeans have always been explorers and how we explore in ESA. I'm sure he has spoken about the fantastic missions we had been able to put together and perform when uniting in Europe. Rosetta, we were the first ones to land on a comet. We Europeans were the first ones to land on a moon outside of the Earth's moon, with the mission that was just plunged into Saturn earlier today. So we Europeans have always explored, and what I'm going to show is how we are preparing for us Europeans exploring also in the future. So you saw probably some of these images. This is one of the last images taken by Cassini before it plunged into Saturn. And I don't know who is owning Saturn. The title of the festival is "Who Will Own Space?" I don't know which part of Saturn I would like to own. I don't know which part of these rings you would like to own. I don't also know what you want to do with it. So who is owning space now? I think we are all owning space. Who is going to own space in the future? Who is going to own the future? I think our children are owning the future. Our children and grandchildren are already owning the future. And we're essentially just here to take good care of what we let them. But what should we tell them? Who is going to be successful in the future? Who is going to own the future in terms of dominating it? I think the answer is the future is really cheap. The future is cheap because it's made out of ideas. It's made out of concepts that emerge just in anybody's brain. And that's one of the main guiding principles we have when preparing for the future via the Advanced Concepts team I have the privilege of heading in ESA. We try to connect to as many brains as we can, because everybody can have the brilliant idea that will change the future. And it doesn't take much. It takes a little bit of time. It takes a little bit of education. But it takes a lot of curiosity. It takes a lot of courage, audacity. So I think the future will be owned, and space will be owned by those who dare, by those who try out different things, by those who are not sticking with what we do currently, by those who are a little bit odd, a little bit outwards, a little bit strange, where you're not sure if it's crazy or if it's maybe genius. And what in our team are looking for, we're looking for the oddballs. and we recruit a lot of these oddballs for limited amount of time. Yes, they have to have a university degree. Most of them have to have a PhD. But we are still looking for the odd ones out, because those are the ones who tell us probably more about the future than the others. So what I'm going to present you in the next few slides, and I'm trying to speak slowly. If there is anything that you don't understand, also give me signs. I don't want to monopolize the evening. I'm happy to also receive questions in between. And I have something like 100 backup slides on different concepts. So in case of questions, I think I'm well prepared in case there's something that we have done on it. So the future is clearly not there to predict. There are a few alleged predictions from gentlemen that I would never dare putting anybody, even anybody in ESA, next to them. They're all eminent scientists. You might recognize some of them. I haven't put their names because their predictions or their alleged predictions didn't come true exactly as predicted. And these are illustrations from the year 1900 about what would be in the year 2000. We're not doing this at ESA either. We are not trying to predict, but what we are trying to do is what Saint-Exupéry so geniusly said, is about the future. You should not predict it, you should try to make it possible. So what we are trying to make possible are different futures, and futures where we think they are good futures for all of us. A completely different way of looking at the future than scientists comes from lawyers and politicians. And this is a lawyer and a politician, a good friend of Winston Churchill. He died in 1930, and just before dying, he published a book which is called The World in 2030. And he had no education to foresee the future in any way, other than being a lawyer and being a politician, which typically is not the people we normally ask for, tell us what the future is. But if you read his book, and you can find it still in antiquariats, he has probably described the most accurate way of any of the science fiction future stories. And he has not talked about technology. He has only talked about human nature and what humans really want and what humans really are up to and why we get up in the morning and what motivates us. And then he has looked at, well, what might be satisfying these needs. And he looked also at trends. And then he looked at emerging technologies that could maybe satisfy these needs. So in this book published in 1930, he, for example, mentioned that very likely, because we all need to communicate, we could communicate from any point in the world to any other point in the world instantaneously in sound and video. There was no technology push at the time that could have made him think this. He died unfortunately very early because he was also of the British upper class, and he was drinking a little bit too much, way too much, unfortunately. So he died out of liver failure. But what he did is what is typically not shown in concepts about the future. We look at our gadgets and we look at how they evolve. He looked at it from the completely different side. So what will we need and how will we want to live, and what does this mean of what type of technologies we are going to develop. I'm not going to follow this path, but we are always trying to keep this in mind when we look at future technologies. And they start typically by looking at scientific advances that have not yet any technological application. And I'm going to explain in the next few slides 3 innovations that come from the 1950s, where I think they have been transformative to our lives today, some already very strongly, some might still to come. It's in analogy to a lecture that the Royal Astronomer Sir Martin Rees gave a few years ago, where he used a very similar concept. And one of these key innovations from the 1950s is, of course, the integrated circuit, the precursor for what is now ubiquitous in all of your pockets. You just switched them off a few minutes ago. Kilby and Noyce made the first integrated circuit, and that allowed the third, fourth industrial revolution that we have now. And that probably, with a continuation of Moore's law, will lead to more and more autonomy. We have now autonomous cars that can drive in cities like Naples, which means there's real autonomy. Immersive, multi-sensory, augmented or virtual reality, ubiquitous sensors, the merger of real and virtual worlds. The second of these innovations from the 1950s is the discovery of the double helix by Watson and Crick. This is the foundation of what we understand of heredity, molecular biology, and they're probably the main impact on our day-to-day lives are not yet clear. So there are also more question marks in there. Biofuels, synthetic biology, human augmentation, enhancement, new forms of life. We have created the first cellular lives that are designed now. Genomic engineering, longevity. And the third one, also from the 1950s, is space. 60 years ago, the first satellite was launched, and it surprised everybody, even those who launched it, especially in the way how it impacted our imagination. And the fact that we saw our Earth from outside completely changed the way how we see borders, how we see ourselves, how we see our place in the universe. It had a huge impact on political movements like environmentalism. We created a number of completely new technologies that you see already now ubiquitous. The first solar cells were developed for the space program because you couldn't have any coal, oil, or gas to burn, and batteries would not last long enough. It had created completely new services, new markets, and it allowed us to have a vision of our impact on the Earth that was completely strange to anybody before this generation. And we are probably going to see in the next few years already the emergence of a new extension of human economic spheres. Now the Earth orbit, so 400 kilometers above us, is the International Space Station. Most Earth observation satellites are just 700-800 kilometers above us. The weather satellites, the telecom satellites, they're at geostationary orbit at 36,000 kilometers. And what we are at the verge of seeing is first daring private industry venturing up to the moon, to cislunar space. And this cislunar economy is completely open yet. We don't know what it is. We don't know how it's going to look like. But it's clear an extension of what we have in Earth. And it's not a discipline. Space is sometimes called, well, this is a discipline. Space is not a discipline. It's also not a science. And space is not rocket science. Space is just another place. Like we discovered the oceans, and we learned a lot about the oceans. We developed loads of technologies for the oceans. We are exploiting the oceans. We are then we discovered how to use airspace, and the lawyers call what we call space, they call it outer space. As a name, everything that is not airspace is outer space. And if you look at the legal text, there's even not yet a definition what is the border between airspace and outer space. There are some conventions, but there's no definition yet. So everything that's not airspace is outer space. But outer space is huge. Outer space is also diverse. Outer space is orbit. Outer space is the moon. Outer space comets. And we don't know yet what it will learn us. We know already how to use it a little bit. We explore here and there. But we will probably see some sort of human outposts in the moon that is very different from what the Apollo area moon exploration was as a showcase what can be done. Our Director General calls it the Moon Village, not a village that has a church and a coffee and a restaurant place and a few houses around. But village because it's not designed by a genius brain like Werner von Braun, but village because everybody brings what he can, everybody takes what it can, it's living together with robots, and everybody can participate to this moon village. It doesn't need to have a master plan where one says that's what we're going to do here and you're going to do that. The moon village is more about interfaces, about enabling different nations, small and large, to contribute. And Poland had its first satellite not so long ago. Poland is absolutely capable of landing something on the moon. Not the same thing as the Americans, maybe, not the same thing as the Russians. But once we are on the moon, we should be able to cooperate. We should be able to help each other. We should be able to communicate with each other. And that's the concept of what he calls the Moon Village, which is inspiring many of us at ESA, most of us, hopefully all of us. But when you look also at the three key innovations from the 1950s, you also see that they are addressing loads of global challenges. Some of them I mentioned already that are addressed by space. The resources, I have a few slides later on about how space has taught us a lot about resource efficiency. In space there is no waste. We cannot, every waste is a liability. So we have to reuse, recycle everything that we can. But I'm not going to go too much into this. But I want to use this slide also as an introduction of how we in ESA try to prepare for the future. So I already mentioned that we are trying to tap into the brains of as many as possible, Europeans and non-Europeans alike. We have adopted a completely open science approach where we ask for ideas, we take them into account, we cooperate with whoever wants to cooperate, many times just based on basic mutual interests. And the second aspect is where we think the new things come from is not at the centers of disciplines, but at the intersection of disciplines, where the biologist meets the fundamental physicist and they need some time to find a common language to speak about their domains. And what I'm going to show you in the next few slides are some examples of what we are currently working on, what we have been working on recently, and some of the outcomes of this work at the intersection of disciplines, where where the different disciplines meet, and where it's not yet clear what this will be, where this will lead to. Sometimes it's a completely new discipline. Sometimes it's just joining forces to do something together that you would not come up with if you stayed in your discipline. So one concept is deep space navigation with pulsars. Something that is a pretty standard idea when you understand what we do with GPS, Galileo, or GLONASS, or Baidu, the Chinese system, which are the global navigation systems. What they essentially do, there are a number of 25, 30 satellites circling Earth, each sending a very precise time signal. You get them, you compare them, and then you know where you are with respect to the satellites and with respect to ground. In space, when we go deep space, we don't have this triangulation. But in space, we have extremely accurate clocks. And these accurate clocks are called pulsars. What pulsars do, they send signals at very, very regular frequencies, and they're all over the sky. So once you know where they are, if you know their timing, and this is just the frequency at which they emit, you can localize yourself. So it started as an idea, very cheap, in the brain of a young scientist. Joined us, looked, of course, into the technicalities first. We made the first few papers, and now this is something that is not yet used, but I'm sure it will be used, because it's something that could be used to go wherever, not only in our solar system, but also beyond. Then something that was science fiction just 10 years ago, when we proposed this, I think 12 or 13 years ago, inside ESA in one of our internal workshops. We got almost kicked out of the room, that we are paid by taxpayers' money and we should not speak about science fiction. It was about changing the course of asteroids. But we pursued nevertheless, and asteroids are very interesting. They are scientifically very interesting because they give us loads of information about how our solar system has been constructed, about the very early stages of this solar system. But we also know that asteroids have impacted Earth in the past, and we also know that they will impact Earth in the future. And we know some of them are pretty large, and we are fairly confident that one of them had done some damage to the dinosaurs. And we know now that this is a threat, and it's a threat that we can do something about. There are some threats where we can do nothing about yet. But asteroids are a threat where we can do something about it. So we have prepared a number of mission proposals. The closest we got to actually getting one funded by politicians was called the mission AIM, which was at the last, what is called the Ministerial Council of ESA. We were very, very close of getting it funded. It was a mission together with NASA. We haven't yet given up. We will try again. Personally, I think this is one of the things that we have to do. We have to do because we have to take good care of the future of our children and grandchildren. And I'm certain that we also will do it. Because we know that we can do things to deflect asteroids, and we just have to go there early enough. We need to test it, and this was a mission to test that we can actually change the trajectory of a small asteroid. Now I tell you a funny story. We typically have always one or two fundamental physicists in the team who don't come from the space field. And we exposed them to the environment in ESTEC. ESTEC is the scientific and technical center of ESA. And this, where you somehow have the collective brain of space in Europe. And when he heard a lecture about the Galileo system, which is the European global navigation system, and he heard that in order to get the accuracy that you need on ground, you need to make relativistic corrections to the signals that you receive, because the satellites move at relative speeds, and these speeds are so high that you cannot have the Newtonian mechanic. You need to take into account Einstein's mechanic in the general relativity. And the way this is done is we add relativistic correction terms, which is working perfectly fine. But for a fundamental physicist, this is, of course, not at all fine, because this is a very, he would call, dirty way of doing. You add relativistic correction terms. When you can do it properly, why do you do it with correction terms? So his question was, well, why don't we do it with an Einsteinian metric? Since 100 years we know the new metric, and why do we use Newton when we could use Einstein? And the answer, of course, was, well, we don't need the full Einsteinian metric, and it looks too complicated anyway. So why should we do? And this, of course, from an engineering point of view, it's absolutely right. You don't need to do fully relativistic metric, which is much more complicated. But what, for a fundamental physicist, this is not at all a good answer. So he went back, and a few weeks later he came back to me and said, look, I think I have found a way of doing this completely relativistic. And I told him, yes, yeah, it's nice, it's good, but why would we? And I said, well, I think there could be also some other advantages than just being neat and clean and using the right physics. You could have your reference time in space by doing so. And putting your reference time in space has a number of advantages. Now we have Galileo ground stations all over the Earth, and we need them because our time references are on ground, and we correct them constantly for tectonic movements. The different continents move relative to each other, so we need to constantly correct the reference time systems. Once you have this in space, you would be independent from this. And as an economic argument, and that was then the argument that helped us going further, was if you need only one ground station per continent to compensate for this, you are much, much cheaper, because ground stations are not very cheap. So we continued doing this. We found a partner in Slovenia. They were very interested in doing these more mathematical, numerical calculations together with us. We published it, got some traction, but what really changed then a few years ago, when we launched 2 of our Galileo satellites from a Soyuz launcher in French Guiana, Kourou, the upper stage put these Galileo satellites in a slightly wrong orbit. We shouldn't say wrong orbit, but not in the intended orbit. And normally they are nicely circular orbits. And unfortunately, these 2 satellites were in elliptic orbits. And so we had to figure out how to still use them within the Galileo constellation. And the very same evening that they were in this, that in the news was announced that Galileo satellite in the wrong orbit, the researcher who initially had this idea called me saying, "Hey, fantastic! Nothing better could have happened to us." And I said, "What are you talking about?" He said, "Well, these satellites are in the perfect orbit to measure some of the Einsteinian theories, the redshift. for example, and time dilations. So what he said is, we have done all the mathematics that you need. You just need to switch on the clocks and you need to measure this and use our system that we have developed for the completely relativistic metric for G and S to measure with an order of magnitude better the relativistic predictions of Einstein than was done previously with gravity probe P. And this is what we have done now. It took us not even 3 weeks to put this in place because the satellite was there. The full mathematics was developed. It's not yet published, but we have fantastic results. We just extended the measurement period for a few more months. And this is a good example of something that was there for completely theoretical purposes to be just mathematically, physically more beautiful, that ended up because of a wrong orbit, because of a failure of an upper stage, to be a very nice scientific experiment. Another thing that we did a lot was we worked a lot on autonomy. And what you see there is just one of these, one example of this research, where we try to learn robots how to judge distances. So when we humans judge distances, we typically use triangulation as our binocular vision to judge how distant objects are. But beyond about 10 meters, 10, 12 meters, we use our judgment of how big objects are, because the triangulation is no longer that accurate. So if you see a mountain, we know it's based on the size, that it's relatively far away. And if you see a tree, we can easily judge how far this is away. So we did a number of experiments, also involving huge amounts of people that have these parrot drones. It's a small game to teach algorithms based on the sizes of objects, how far they are away. And this is a video where you see these spheres. These spheres are originally educational purposed small balls that are on the International Space Station. And we taught them the first time how to learn distances in space autonomously. Now, global optimization is something that is used in almost all space missions, especially those that go further out. And what you see there is a trajectory that humans can no longer design. So almost all trajectories up to, well, 10 years ago have been designed based on human intuition of the mechanics of the solar system. So where planets are when do you launch, when you fly by Jupiter, Venus in order to go with the least amount of fuel to wherever you want to go. And if you look at the trajectories of, for example, the Voyager missions, you see that they have passed many different planets. But this was done based on human intuition. What we have started looking at was, can't we find algorithms that are much better than humans in finding the global optimum, where a global optimum you cannot get mathematically? And so we introduced, as an example of reaching out to whoever is interested in algorithms, we made a competition. The first competition was about 10 years ago, and saying, well, this is a problem, we don't know the optimum. Whoever, and this is the objective function that gives you the optimum, whoever is giving the best solution gets a prize and is there to organize the follow-up competition, like the America's Cup. So the first competition was won by GPL, and then the University of Torino. I don't remember. Then it was again GPL, I think. And it's now an annual competition where loads of even students can participate. We provide all the tools. You just have to find a very good algorithm that is smarter than all the other algorithms. And now let me show you this. The left image is slightly awkward. It comes from the Oxford Spider Lab, and it is a good example of how disciplines merge. You see Tom Ryns on the left, the Belgian biologist who did his PhD with spiders, and on the right, Isabelle, a Canadian laser physicist, and they both joined the team, and we ask all researchers to come up with things that are new and that somehow at the intersection of disciplines. Now, when Tom spoke about how spiders use the changes in the spider silk in order to sense the quality of the atmosphere, and he said, well, once you technicians will be able to do what a simple spider can do by sensing the silk, I will no longer be here. And that was, of course, not a satisfying answer for Isabelle, who said, well, if a spider can sense a spider silk, then we could also sense it with a laser, for example, because what actually the spider does, it looks at protein changes in the silk. So we looked at how much you can actually get this spider silk in a reliable way, and apparently what you see on the left image there, it's highly reproducible. They have these spiders in the room, they feed them, and from time to time they milk them in a standardized way. So we teamed up with Oxford and EPFL, Laser Lab, and we shipped some of these spider silk to the laser guys in EPFL and said, could you please cut it and shine a laser through it? And they couldn't figure out how to handle the spider silk in the first place, because it's much thinner than the typical optical fibers that they are used to. It took us about 4 or 5 months to find out a way of doing this. But what you see in the upper picture is an extreme, so you see this spider silk that is the strings, and you shine a laser from one side, you have a detector on the other side, and you could actually measure that you can detect very subtle changes in the atmosphere via just detecting how the light is slightly modified when going through this spider silk. So what you see there, the guy is just blowing in there, and what we are looking for there is eventually using this on Mars, because it's an extremely sensitive methane sensor. And methane is, of course, of interest for Mars because it's a sign of life. And we know that there are some indications that there is methane on Mars, but it's very sparse. So if we could find a way of detecting methane, the advantage of detecting it via such spider silk is that it is self-cleaning, while most of the other options of using laser fibers, you have to have certain cleaning techniques and procedures, while this spider silk is extremely reliable. Then, when another example from biology, so we recruit always biologists who have no connection to space, and we put them into a space environment and we ask them to tell us about advances in biology. And one of these things is insects, bees and flies, and but we looked specifically at bees. They have a very, very reliable way of landing in completely awkward environmental conditions. And landing is one of the most complicated things that we have in space. It requires loads of computational power. It requires autonomy because you can no longer react in real time. We had a number of failures because of landing. And then you have these insects who have a brain of a few milligram, and they land reliably on the very difficult wind conditions, on the very difficult illumination conditions, on moving objects. They crash relatively seldomly. And the question is, how do they do this? While we need 3 parallel computers, and we do majority voting of computers, and we take all types of different sensory inputs. And could we have just some sort of an equivalent of an insect brain as at least as a backup option? So fortunately, there was a paper published about 10 years ago of a neurologist who was studying the optical system of bees. So he published a paper describing from A to Z how the bee actually processes optical information for biologists. And only because you have a biologist in the team, he would even read the paper and then say, well, there is something. If we now know how the bee does it, well, in principle, we should be able to put it also onto an artificial system. So what we tried out with the University of Marseille, a small toy helicopter. And actually it turns out the bee doesn't know how high it flies. The bee only knows what is called the optical flow. It only knows how fast patterns pass through their eyes. And via this, by keeping this optic flow constant, it can land on almost any object as long there are patterns that pass by. So what we then did, so we demonstrated that in principle this is possible. It's completely analog, so you don't need fast processors. So it's a system that that you can implement with just an extremely small cube. We are now looking into putting this eventually into a lunar lander as a backup system. Backup for the simple reason that it's not optimal. So it's extremely robust, but it's not fuel optimal, how this system would look like. But it's a very good example of somebody who needs to go slightly outside of his own field, or looking for solutions that you would normally not find when you don't ask a biologist to look at how to land on a planet or on a moon. Now, I want to show now a few slides, 3 slides about energy systems. And what you see there is a percentual representation of where our energy comes from, our power sources, to be correct. And you don't see absolute values, you see only relative values. And we started, of course, on the lower right side. This is where humanity lived for thousands of years. We used renewable power sources, wind, water, biomass burning. And only with the industrial revolutions we started shifting from renewables to coal burning. So in the 1920s, after the First World War, we used almost 80% of our energy came from coal burning. With the invention of the internal combustion engine and the discovery of oil and gas, and you see there Churchill converting the British Navy from coal to oil. What you see, the 20th century was essentially fueled by oil and gas. Up to the leveling in the 1970s, when the oil crisis changed, and we introduced nuclear power to the levels where we have still now. We haven't changed much since then. But when you look at this, and you also know that this is the area that is essentially unsustainable. We know that we still have resources, we have a number of resources, we always find new resources. But this is the part that is the unsustainable area. Jimmy Carter tried to launch an initiative just before leaving office, 20% solar in 2000. Ronald Reagan took off the solar panels from the White House as soon as he came into office, and also stopped this program. But in space, we're exactly there where we need to go also for our terrestrial system in the long run, which is the lower right corner. So we use renewables almost always. There are a few missions, and Cassini-Huygens is one of them, where we had to use nuclear batteries because we were too far away from the sun, and there was no other option than to use nuclear batteries. But typically, we need to use renewable energy sources, and if you want to find an energy-conscious engineer, the space sector is one of the best places you can go to, because every watt, every milliwatt is counted for. Now, we use solar power in space for space, but here we are talking about the future. We have abundant amount of solar power on Earth, but we have even more solar power in space. And the question is, we have increased the power levels on our satellites from 5 milliwatt. This was the first satellite, Vanguard 1, that used actually solar power in space with custom-made solar cells. In '58, the International Space Station is now using about 100 kilowatt. And if you multiply this a little bit further and you strip all the payload while we actually generate electricity, and you make a satellite only out of solar panels and a transmitting antenna, you have something that is called a solar power satellite. And it has a number of advantages. There is no day-night cycle. It's always there. It would provide the baseload power. You would not need storage on Earth. You can transmit it. We have tried it a number of times. We know since the 1970s that you can transmit it wirelessly via microwave. We have made huge advances in transmitting it also via laser. And eventually one day we will use solar power from space to receiving stations in Earth. You see there some videos how this could look like. Essentially, it's huge solar panels with a relatively large antenna, large in space so that you can keep the terrestrial antennas not too large. There are different concepts there. It is something that is not yet there. The economics are not yet feasible. But technically, this is something we can do. We know we can do. And therefore, probably one day we will do it. What we have done is a small, cheap, early demonstration of one subsystem. And that is the antenna part. So you need relatively large antennas, and we don't want to construct antennas with astronauts with bolts and screws. So we looked into how you could make some small robots that crawl on a free-floating net that is spanned in space. We teamed up with two Japanese universities, launched a small sounding rocket, deployed a spider web, and then made a few robots crawl on this net in view of having them as mobile antennas in the future. You see there are a few microgravity videos of different concept of how these crawling robots on a spider net could look like. They would be then the individual antenna elements. And then I want to go even one step further and tell a story about hamsters and bears. We got a question a few years ago about what's the ESA position for or on hibernating astronauts for long distance space travel. And we didn't have a formal ESA position for hibernating astronauts. But when looking at the question, we thought, well, is this pure science fiction or is this something that we should have a look at? And at the time, we found a number of interesting researchers, nice papers, and but it was not mature enough. It was in 2006. But then a few years later, what was also discovered by biologists is that these hibernating animals, they use this hibernating state, which has nothing to do with sleep. In the German language, we call it Winterschlaf, which is sort of a sleep of winter. But it has nothing to do with sleep. It's a completely different state of the organism. They use it as an energy-saving organism. It has also nothing to do with temperature. There are animals that are hibernating at over 30 degrees, 37 degrees, some lemurs in Madagascar. It has nothing to do with temperature. The main purpose is resource scarcity and energy saving, so resource saving. And what this paper I mentioned showed is a German researcher who showed that these hibernating animals, they use 90% of their energy during hibernation, during short phases where they wake up. And they're actually not waking up, they're arousing from this hibernating state. And guess what they do when they arouse from this hibernating state? Any good guesses? Read? Breathe? No. They breathe very slowly also during hibernation, so the organism doesn't stop. But no, they don't breathe. P would also have been my guess, but it's also not. They also don't eat, they don't drink, they don't pee. What they do, they sleep. So they spend 90% of the energy in an energy conservation mode to sleep. And that triggered a number of questions, of course. What's happening when you don't let them sleep? So when you wake them up during these things, and they get completely crazy. And then we looked at, with a group in Oxford, we looked at what sort of sleep is this? And it turns out that this is a type of sleep where the different brain regions synchronize. And astronauts sleep very badly. Astronauts sleep about an hour less than the average human. And it triggered a number of connections. Initially, we were looking at hibernation for reasons like these animals don't lose their bone mass. So they are not using their bones, but they are not losing their bone mass. They are not using their muscles, but they are not losing their muscle mass. And they are higher. They have a higher resistance to radiation levels. All three elements are of interest for us for long-distance space travel, because astronauts now, they need to spend 2.5 hours every day just to train to not lose bone and muscle mass. And radiation is one of the biggest unsolved issues for even travel to Mars. So having their animals that we know they don't lose bone, they don't lose muscle mass, and they are more resistant to radiation. That was our initial motivation. But then when we found out that they are sleeping when waking out from hibernation, and the type of sleep they are doing is insofar interesting because it's the type of brain state that all of you can put yourself in when you do regular movements like bicycle or walking in an environment that is not stimulating you overly. So it's the type of mode that you get into when you walk somewhere along the river, on the beach, or in the forest. And you might have noticed that after something like 15, 20 minutes, you get strange, you get ideas, you think about things differently than when you started. And that's the state of the mind when different brain regions are synchronized. And what we are looking now is if we can use these exercises, and there is one component that is always there. It needs to have a physical component, a repetitive physical movement. If you can use these exercises to reduce the sleep need of astronauts, so that they can maybe better sleep and need less sleep and reduce some of the sleep medication. Now, why do we think that maybe humans could hibernate? Well, there is a strong indication that humans should have the capacity to hibernate. And where does this come from? This comes from looking at the mammalian tree. So when you look at the evolution of mammals, we all come from a common or a few common ancestors, and then we were split up into different mammals, and now there is a large category. It is always revised by biologists with small refinements, and there are a number of subcategories in there, and there is a natural hibernator in each of the subcategories, and there are many hibernators they are not naturally hibernating, but you can induce hibernation by just reducing the resources that these animals have. And this is an indication that the biological capacity of hibernating is older than the split of this tree. And we are just one of the species in this tree. So in principle, we should be able to hibernate. And there is ongoing research in some medical fields on looking at what is the actual mechanism at the cellular level for the start of hibernation. So with this, which is not for tomorrow, which is not for in 5 years, it's probably not for in 10 years, but some of the discoveries when looking at hibernation, for example, the sleep one, they're probably there for already tomorrow. I want to finish with a few images from our artist in residence. This is one of the things that we introduced a few years ago. We started with mainly scientists, including biologists, and we added also some more social scientists. And since a few years we also have an artist in residence in the team, because he looks at the world very differently and he enriches the way how we look into what the future could look like. So what he envisaged there, and you don't see too well up here, is some sort of a lunar dome. He called it the temple, a lunar temple. So he imagined what would be a sort of structure that people would construct on the moon, where they want to somehow get together. How would it look like? He got inspired by by structures that were made in Middle America before Columbus arrived. And then he looked at what sort of objects might humans want to have as not utility objects but artistic objects, and how would they look like once you are living for a long time, or maybe even you grew up in an environment that is not showing you trees and rivers and flowers, but it shows you spacey materials. And well, he came up with some what he called lunar artifacts. He made a story out of it that future civilizations came back to the moon and found lunar artifacts of an ancient lunar constellation. And with these, I would like to thank you for your attention. As I said, I have something like 80 slides on very different topics, so I want to dedicate the last, I think I still have something like 20 minutes to questions that you might have about future of space activities, other topics that we look at. If you have already looked at it, I'm happy to go into details of any of them. But never forget that we are all living on this pale blue dot, and we have to share it. We have to keep it in good shape, because the future is not ours, but we just preserve it, and we need to keep it for our children and grandchildren, and we all have to live on this small blue dot. Thanks very much.